All right, let's get into this. Imagine you're a farmer back in the 19th century, Northern Europe, and you keep stumbling across these giant boulders, just huge rocks sitting in the middle of your field.
Right, and they're completely out of place, yeah.
Yeah.
Nothing like the local bedrock for hundreds of miles.
Exactly. So these became known as wandering rocks, or erratics, a real geological puzzle back then.
And the first idea, the sort of go-to explanation was, well, it had to be a massive flood, right? Something biblical almost.
It seemed like the only force powerful enough to move these things, and the sediment they were found in, it was all jumbled up, big rocks, small pebbles, sand, mud.
Yeah, not sorted like river deposits at all. It was what geologists call poorly sorted or even diamicton. It just looked like chaos.
Total chaos. But then you get this Swiss geologist, Louis Agassiz. In 1837, he'd been studying glaciers up close in the Alps.
Living, moving glaciers, rivers of ice.
And he looks at this jumbled debris in the Alps, the stuff left behind by actual glaciers, and he has this incredible insight.
He realizes that ice, slow-moving ice, is perfectly capable of picking up and carrying absolutely everything. Huge boulders, tiny clay particles, all frozen together.
No sorting required. It just dumps everything when it melts.
Precisely. So Agassiz looks at the erratics and the messy deposits across northern Europe and says, wait a minute, this wasn't a flood, this was ice.
But not just valley glaciers like in the Alps. He proposed these enormous continental ice sheets, glaciers covering vast areas.
He basically invented the concept of an ice age, a time when Earth's climate was much, much colder, and these ice sheets were way more extensive.
You can imagine the reaction, right? People must have thought he was, well, a bit out there.
Oh, definitely. It was a radical departure from the flood theory. But Agassiz was persistent. He basically said, don't just argue with me, go look.
Go see the evidence in the Alps for yourselves. See what modern glaciers leave behind.
And, slowly but surely people did. By the late 1850s, the idea started to gain acceptance. This notion that Europe, Northern Europe anyway, once had an almost Arctic climate.
And he later came to North America and found the same kinds of features, didn't he? Polished rocks, erratics, U-shaped valleys.
He did indeed, proving it wasn't just a local European thing, it was a global phenomenon. So those puzzling wandering rocks were, in fact, direct evidence of these immense, slow-moving ice masses.
It's amazing how science works, isn't it? Observation, challenging assumptions.
Absolutely. And it hammers home that Earth's climate is not static. It changes, sometimes dramatically.
Ugh.
I mean, think about it. Today, glaciers cover about 10% of the land.
Okay.
But at the peak of the last ice age, maybe 20,000 years ago, it was closer to 30%.
30%? Wow. So places like New York City, Montreal, they were buried.
Buried under potentially kilometers of ice. It's quite sobering.
It really is. Okay, so for this deep dive, we're going to properly explore glaciers and ice ages. We need to understand how ice itself works, how glaciers form and flow.
How they carve up the landscape, the kind of evidence they leave behind.
Yeah, erosion, deposition, and then what actually causes these massive ice ages to happen in the first place.
It's a huge topic, but fascinating. Let's start with the basics. What exactly is ice?
Right. Solid water, obviously, H2O.
But it's crystalline, isn't it? It has a specific structure.
Yeah, a very orderly arrangement of those water molecules. It forms a hexagonal crystal lattice. I mean, think of a snowflake, that perfect six-sided symmetry.
Right. And it's interesting, you can draw analogies to rocks, like fresh snow is kind of like loose sediment, right?
Okay, yeah, just accumulating.
And then if you compact that snow, squeeze it together, it starts to resemble sedimentary rock.
Makes sense. What about ice on a pond?
Pond ice, because it freezes directly from liquid water. You could maybe think of it as analogous to an igneous rock crystallizing from magma.
Okay. So where does glacial ice fit in?
Glacial ice is metamorphic.
Metamorphic. How so?
Because it doesn't form directly from liquid. It forms from pre-existing ice snow that gets buried, compressed, and recrystallized under immense pressure over really long timescales. The ice crystals change, they grow, they interlock.
Ah, like rock changing under heat and pressure deep in the earth.
Exactly the same principle, just, much lower temperatures. And you know how glacial ice often looks white or even blue?
Yeah, why is that? Pure ice is clear, isn't it?
It is, but glacial ice is full of tiny air bubbles and microscopic fractures that scatter the light, making it look white. The blue tint comes from the way the ice absorbs light. It absorbs the red part of the spectrum more strongly than the blue part.
So the blue light gets transmitted or reflected back to our eyes.
Cool.
And it's very reflective, right?
Albedo.
Very high albedo. Like wearing white on a sunny day, it reflects a lot of solar energy back into space, which is actually a really important factor in climate. More ice means more reflection, which can lead to more cooling, a feedback loop.
Got it. What about the fact that ice floats? That always seems weird for a solid.
It's incredibly unusual. Most substances get denser when they solidify, but water, well, the way the molecules arrange themselves in that hexagonal crystal lattice actually forces them slightly farther apart than they are in liquid water.
So it expands when it freezes?
Yep, makes it less dense. And that's absolutely crucial for life. How so?
Because it means lakes and oceans freeze from the top down. The ice forms an insulating layer on the surface, protecting the liquid water underneath. If ice sank, oceans could freeze solid from the bottom up.
That would be bad. Very bad for life.
Catastrophic. We owe a lot to that weird density property.
Okay, and the slipperiness. Why is ice so slippery? Is it the pressure melting thing?
That was the classic explanation, yeah. That the pressure from your skate blade or foot melts a thin layer of water. And that does happen to some extent near the melting point.
But it's slippery even when it's really cold, right?
Exactly. So pressure melting isn't the whole story. The modern understanding is more about the surface molecules. Even well below freezing, the outermost layer of water molecules aren't fully locked into the rigid crystal structure.
They're sort of loose.
Kind of quasi-liquid, they have more mobility, creating this intrinsically slippery surface layer. It's a fascinating area of physics, actually.
Huh. Okay, so that's ice. Now, how do you go from snowflakes falling to a massive moving glacier? It can't be quick.
Definitely not overnight. You need a specific set of conditions, and they need to persist over a long time.
Like what? Number one must be cold, right?
Absolutely. Cold enough that the winter snow doesn't all melt away in the summer? Year-round survival of snow is key.
Makes sense. What else?
You need enough snowfall to begin with. Significant accumulation over many, many years. Just being cold isn't enough if it barely snows.
Right. You need the raw material.
Then the slope of the land is important. It needs to be gentle enough that the snow doesn't just slide off in avalanches all the time.
Too steep and it won't build up.
Exactly. And finally, ideally, you need some protection from the wind, which can just blow the snow away before it has a chance to accumulate and transform.
So cold, snowy, not too steep, not too windy. That points to polar regions and high mountains, I guess.
Those are the prime locations, yes. Polar regions are obviously cold enough year-round, even if snowfall isn't massive everywhere. Mountains work because temperature drops with altitude.
The higher you go, the colder it gets.
Right. So even near the equator, if you go high enough, typically above 5 kilometers or so, you can find conditions cold enough for glaciers. Think Mount Kilimanjaro, though its glaciers are sadly shrinking fast.
But at high latitudes, like in Alaska or Norway, glaciers can reach all the way down to the sea.
They can. The elevation needed for glacier formation gets lower and lower as you move towards the poles. So yeah, you can see glaciers calving into the ocean on a cruise ship up north. But you need a serious climb near the equator.
And within mountains, do they prefer certain slopes?
They do. They often favor slopes that are sheltered from the wind, the leeward side, and also slopes that get less direct sunlight, like north-facing slopes in the northern hemisphere. And again, not too steep, generally less than 30 degrees, otherwise avalanches dominate.
Okay, so the snow lands, it sticks around year after year. How does it actually turn into solid ice?
It's a slow transformation process. Fresh snow, it's incredibly fluffy. It's mostly air, maybe 90% air trap between those delicate hexagonal crystals.
Like styrofoam packing peanuts.
Huh. Good analogy. Over time, those sharp points and edges on the snowflakes start to get rounded off. This can happen through sublimation ice turning directly into vapor, or cycles of slight melting and refreezing.
So they become less feathery, more like little balls.
Kinda, yeah. And as they round off, they can pack together much more tightly, squeezing out some of that air.
Okay, getting denser.
Then, as more snow piles on top, the pressure increases significantly on the buried layers. This pressure causes melting right at the points where the ice grains touch each other. It's called pressure solution.
Melting under pressure.
Yeah, the water molecules migrate away from those high-pressure contact points and refreeze in the pore spaces between the grains. This gradually transforms the snow into a denser granular material called firn.
Firn, F-I-R-N.
That's right. Ferns still have quite a bit of air, maybe 25%, but it's much more compact than snow. It's like packed old snow that's survived a summer melt season.
And the final step to glacial ice.
The pressure continues to increase as it gets buried deeper. Eventually, the firn grains themselves start to melt at their contacts, and that meltwater reflazes, filling in almost all the remaining air spaces. The grains recrystallize and grow together, forming a solid, interlocking mass of ice crystals.
With very little air left.
Much less. Maybe less than 20% trapped as little bubbles within the ice. And that's glacial ice.
How long does all that take? Snow to firn to ice.
It really varies. Depends a lot on snowfall rate and temperature. In places with really heavy snowfall, it might only take a few decades, maybe tens of years.
That's faster than I thought.
But in really cold, dry places, like parts of Antarctica where snowfall is low, it can take hundreds or even thousands of years.
Wow. So the ice deep down in those big ice sheets must be incredibly old.
Oh, absolutely. In an average mountain glacier, the ice might be 10,000 years old at, say, 250 meters depth. But in the really thick parts of the Greenland or Antarctic ice sheets, down near the bottom, maybe 2 or 3 kilometers deep, the ice can be hundreds of thousands of years old.
Well, like layers in a cake, recording time.
Exactly. Ice cores drilled from these sheets are invaluable climate records. You can see annual layers analyze trapped air bubbles for past atmospheric composition. It's amazing.
Incredible. Okay, so we have glacial ice. Now, you mentioned mountain glaciers and continental glaciers. Are those the main types?
Those are the two fundamental categories, yes. Mountain glaciers, or alpine glaciers, are, as the name suggests, confined to mountainous regions. They flow downhill, guided by the topography.
And continental glaciers?
Those are the giants, also called ice sheets. Vast, thick blankets of ice covering huge areas of continental crust, thousands of square kilometers, essentially burying the underlying landscape.
So Antarctica and Greenland today.
Those are the only two modern examples of continental ice sheets. But during the ice ages, they were much more widespread across North America and Eurasia.
Let's stick with mountain glaciers for a sec. Are there different kinds within that category?
Yeah, we subdivide them based on their shape and location. You have cirque glaciers, which are small glaciers nestled in those bowl-shaped hollows, or cirques, high up on mountainsides.
Okay, like the starting point.
Often, yeah. Then you can have mountain ice caps, which are larger domes of ice covering the peaks and ridges, maybe submerging some of the underlying topography.
Bigger than a cirque glacier.
Right. Then the classic one is the valley glacier, a river of ice flowing down a pre-existing valley, often for many kilometers.
Like the ones Agassiz studied in the Alps.
Exactly. And finally, if a valley glacier flows out of the mountains onto a flatter plain, it can spread out into a lobe shape. That's called a piedmont glacier.
Got it. Cirque, ice cap valley, piedmont. And they vary a lot in size.
Hugely. From hundreds of meters long for a small cirque glacier to hundreds of kilometers long for some of the big valley glacier systems in places like Alaska or the Himalayas.
Okay, now back to the continental giants. Antarctica and Greenland, how thick are they?
They are incredibly thick, up to about 3.5 kilometers, so over 2 miles thick in central Antarctica. They tend to thin out towards their edges, their margins.
And they just spread outwards under their own weight.
Pretty much. They might develop lobes at the edge where the flow is faster in some areas than others. And it's worth pointing out, Antarctic ice mostly rests on land, though there are huge subglacial lakes underneath, like Lake Vostok.
Water under all that ice.
Yeah, kept liquid by geothermal heat and pressure. But the Arctic ice at the North Pole, that's different. That's mostly sea ice floating on the ocean, not a land-based ice sheet.
Right, important distinction. And you mentioned Mars earlier, ice caps there too.
Yep, Mars has polar ice caps, mostly water ice mixed with dust, with a seasonal layer of frozen carbon dioxide dry ice on top.
Fascinating. Okay, one more classification. Thermal conditions. You said temperate versus polar.
Right, this relates to the temperature within the ice. Temperate glaciers are those where the ice is at, or very close to its melting point, at least for part of the year.
So they might have liquid water within them.
Exactly. Thin films between ice grains and often liquid water at the base, where the ice meets the ground. That's why there's something called wet-based glaciers.
And polar glaciers.
They're in much colder regions. The ice temperature stays well below freezing all year round, right down to the base. They're essentially frozen solid throughout.
Dry-based. Makes sense.
And crucially, this affects how they move. Wet-based glaciers can slide more easily. It's also possible for a single large glacier to have both wet-based and dry-based zones.
Okay, so that leads perfectly into movement. How do these massive things flow? Agassiz put stakes in the ice.
He did. His stake experiment was brilliant. It showed the ice moved and that the center moves faster than the sides. Nowadays, we use GPS and time-lapse photography. You can really see them creeping along.
So what's actually happening inside the ice or underneath it to make it move?
There are two main mechanisms. The first is internal plastic deformation.
Plastic, like bending without breaking.
Sort of, yeah. Below about 60 meters depth, the pressure from the overlying ice is so great that the ice itself starts to deform slowly. The crystals within the ice can change shape or rearrange themselves. Water molecules break bonds and reform them, allowing the ice to flow like a very, very, very thick fluid.
So it's oozing internally.
In a way, yes. Microscopic slip can happen along grain boundaries too, especially if there are thin water films in temperate ice. It's much easier for ice to deform plastically than for solid rock, which needs much higher temperatures and pressures.
Okay, that's the deep ice. What about the ice near the surface, above 60 meters?
Above that brittle plastic transition zone, the ice behaves more like a solid. It's brittle. So instead of flowing smoothly, it cracks when it's stressed.
And that's where crevasses come from, those big cracks.
Exactly. Crevasses are the result of brittle failure in the upper ice. They can be huge, hundreds of meters long, tens of meters deep, several meters wide.
Then dangerous, right? Especially if they're hidden by snow.
Extremely dangerous. Snow bridges covering crevasses are a major hazard for mountaineers and glacier travelers. They often form where the glacier flows over steps or bumps in the bedrock underneath, stretching the upper ice.
Okay, so internal deformation in the deep ice, cracking at the surface. What was the other mechanism?
Basal sliding. This happens primarily in those temperate, wet-based glaciers we talked about.
Where there's water at the bottom.
Right. If there's liquid water, or even a slurry of water and fine sediment, at the base of the glacier, it acts like a lubricant. It reduces friction between the ice and the bedrock or sediment underneath, allowing the entire glacier to slide downhill.
Like slipping on a wet floor.
Pretty much. And that basal water can come from surface meltwater draining down through cracks, or from melting at the base due to geothermal heat coming up from the earth, or even melting caused by the pressure of the ice itself.
So wet glaciers move by both internal deformation and sliding, while dry polar glaciers mostly just deform internally.
Generally, yes. Basal sliding can significantly speed up a glacier's movement.
So what's the ultimate reason they move at all? Just gravity?
Fundamentally, yes. Gravity pulls the immense weight of the ice downhill. When the gravitational force component along the slope overcomes the internal strength of the ice and the friction at the base, it flows.
And the direction is always downhill.
Well, the surface of the glacier slopes downhill, and that dictates the overall flow direction. Valley glaciers flow down valleys. Ice sheets flow outwards from their thickest, highest point.
But you mentioned the base. Can the ice at the bottom flow uphill?
Locally, yes, because the pressure from the thick ice upstream can actually squeeze the basal ice up and over obstacles or bumps in the bedrock underneath. Think of pancake batter spreading on a griddle. It flows outwards, even over slight irregularities. Ice sheets spreading under gravity is a similar concept.
The pancake batter analogy helps. Okay, how fast are we talking? Is it really glacial pace?
Usually, yes. Typical speeds are somewhere between 10 and 300 meters per year. So maybe a foot a day, give or take. Much slower than a river, obviously, but way faster than tectonic plates moving.
What makes one glacier faster than another?
Several things. Steeper surface slope generally means faster flow. Ice temperature matters a lot warmer. Temperate glaciers flow faster because the ice is weaker and they benefit from basal sliding.
And friction.
Friction plays a big role. The ice in the center of a valley glacier moves faster than the ice along the sides and bottom, where it drags against the rock. Same vertically, the surface moves faster than the base.
Are there ever times when they move much faster? I feel like I've heard of that.
Absolutely. You get features called ice streams within the big ice sheets. These are like fast lanes, often wet-based, where the ice can flow 10 to 100 times faster than the surrounding ice.
Wow. Fast lanes in the ice sheet.
And then you have glacial surges. These are relatively short-lived events where a glacier suddenly speeds up dramatically, maybe moving 10 or even up to 100 meters per day.
Per day. What causes that?
It's usually linked to a sudden buildup of water pressure at the base. The water lifts the glacier slightly off its bed, drastically reducing friction, and it just kind of takes off. These surges can sometimes even cause small earthquakes called icequakes.
That's wild. So the ice is moving, sometimes slowly, sometimes fast. Does it always move in straight lines?
Not usually, no. The flow paths within a glacier are often curved. Ice gets buried in the upper part, flows down and outwards, and then can actually rise towards the surface near the toe, especially in the ablation zone where the surface ice is being removed.
Why is that important?
It means things picked up by the ice at its base, deep down, can eventually reappear at the surface near the front edge. That's why, for example, scientists find concentrations of meteorites on the surface in certain areas of Antarctica. They land all over, get buried, flow with the ice, and then get concentrated as the ice ablates away near the margin.
like a natural conveyor belt bringing buried treasures to the surface. Okay, so glaciers flow. We also hear about them advancing and retreating. Does the ice actually flow backwards when it retreats?
Ah, good question. No, the ice itself always flows forward, downhill, or outwards. Think of it like a bank account.
Okay, I like analogies.
Accumulation is snow falling, adding mass that's your deposits. Ablation is ice loss through melting. Sublimation, ice turning directly to vapor, or calving, breaking off icebergs. Those are your withdrawals.
Got it. Income versus expenses.
Exactly. The upper part of a glacier, usually at higher elevation where snowfall exceeds ablation, is the zone of accumulation. The lower part, where ablation exceeds accumulation, is the zone of ablation.
And the line between them.
That's the equilibrium line, roughly where accumulation equals ablation in an average year. Now, the ice flows from the accumulation zone down into the ablation zone.
Always flowing towards the front edge.
Always. The path is generally concave upwards. Ice gets buried up high, flows down, and then moves towards the surface down low as the overlying ice disappears.
So if the ice is always flowing forward, what makes the toe advance or retreat?
It's all about the balance. If accumulation income is greater than ablation expenses over time, the glacier gains mass and the toe advances forward, pushing into new territory.
The glacier gets bigger and longer.
Right. But if ablation is greater than accumulation, the glacier loses mass and the toe retreats back towards the source.
Even though the ice is still flowing forward towards the toe?
Yes. It's just melting or calving away faster than new ice is arriving from upstream. Think of walking forward on an escalator that's moving downwards faster than your walk. You're moving forward relative to the steps, but backwards relative to the building.
Okay, that makes sense. The position of the front edge depends on the net budget, not the flow direction itself. What happens when glaciers reach the sea? That's where icebergs come from, right?
That's right. When a valley glacier flows into the ocean, it's called a tidewater glacier. Sometimes they form floating extensions called ice tongues.
And the big continental glaciers.
When they reach the sea, they can form vast, flat, floating sheets of ice called ice shelves. Think of the huge Ross Ice Shelf or Ron Ice Shelf in Antarctica.
Do they always float?
In shallow water near the coast, they might be grounded resting on the seabed. But in deeper water, they float. And because ice is less dense than water, about 4/5 of the ice mass is actually below the waterline.
Only the tip of the iceberg is visible.
Literally. And calving is the process where chunks break off the front edge. If the chunk is big enough, generally defined as at least 6 meters above water and 15 meters long, we call it an iceberg.
Are there names for smaller pieces?
Yep. Smaller ones are called bergy bits, maybe 1 to 5 meters above water. And even smaller chunks are growlers, less than a meter high, apparently named because they can make a sort of growling sound as air bubbles escape when they melt.
Growlers. Love it. Where do the biggest icebergs come from?
Mostly from the edges of the Greenland and Antarctic ice sheets. Icebergs from valley glaciers are often irregular, maybe jagged or pinnacle-shaped, but the ones breaking off the big Antarctic ice shelves are often massive and flat-topped tabular icebergs.
Like that huge one from the Larsen Sea ice shelf a few years ago.
Exactly. Those can be enormous, the size of small countries sometimes.
And tragically, icebergs can be dangerous, the Titanic.
A stark reminder, yes. Icebergs, especially hard-to-see ones at night or in fog, are a serious hazard for shipping in certain waters.
Now, is all the ice in the ocean from glaciers? What about sea ice?
Good point. Yeah. Sea ice forms directly from the freezing of ocean water itself in polar climates. The Arctic Ocean is mostly covered in sea ice, and there's a lot around Antarctica too.
Is it different from glacial ice?
Yes, it's generally much thinner, and it contains salt trapped during freezing, unlike freshwater glacial ice. Some sea ice melts and reforms seasonally, some persists for years. Multi-year ice. And ships called icebreakers are needed to get through it.
And we're seeing less sea ice now, especially in the Arctic?
Sadly, yes. The decline in Arctic sea ice extent and thickness, especially in summer, is one of the clearest signs of global warming. We're also seeing Antarctic ice shelves thinning and breaking up more rapidly.
So these icebergs floating around, they carry rocks and stuff, right? Drop stones.
They do. As glaciers flow over land, they pick up rocks, gravel, sand, mud, all frozen into the ice. When an iceberg calves off and drifts away, it carries that debris with it.
And drops it when it melts.
Exactly. This sediment dropped from melting icebergs onto the seabed is called glacial marine sediment. And when you find isolated large rocks dropstones sitting in otherwise fine-grained deep-sea mud, it's a very strong clue that icebergs were once floating overhead. It's key evidence for past glaciation.
Okay, so glaciers transport stuff, but they also do a lot of carving, right? Shaping the land.
Oh, massively. Glacial erosion is incredibly powerful. Think about Yosemite Valley in California.
Huge U-shaped valley.
Right. That area started as granite formed deep underground, part of the Sierra Nevada batholith. Uplift brought it to the surface, rivers carved V-shaped valleys. But then the ice ages came.
And the glaciers just bulldozed through.
They did more than bulldoze, they sculpted. They quarried and ground away the rock, widening and deepening the valleys, steepening the walls, creating that classic U-shape. Features like Half Dome got their sheer faces from glacial action.
And those sharp ridges and pointy peaks in the Alps and other big mountains.
Also glacial work. Knife-edged ridges called arêtes formed where glaciers eroded back-to-back valleys. Pointed peaks called horns, like the Matterhorn, sculpted by glaciers gnawing away on multiple sides. Glaciers are so effective at eroding high mountains, some call it the glacial buzzsaw, they can actually limit how high mountains can get over geological time.
A buzzsaw. Wow. Do continental ice sheets also erode much? They seem flatter.
They do, just differently. They
Yeah.
can strip away soil and loose rock over vast areas, exposing the underlying bedrock. Think of the Canadian Shield. Huge areas scoured clean, sometimes removing tens of meters of material.
So how do they actually erode? What are the mechanisms?
There are several key processes. First, in mountains, rocks fall onto the glacier from the valley walls, aided by freeze-thaw action, breaking up the rock. But the main action happens at the base.
Where the ice meets the ground.
Yeah. One is glacial abrasion. Rocks and grit embedded in the bottom of the ice act like sandpaper, grinding against the bedrock as the glacier flows.
That must create a lot of dust.
It does. Very fine sediment called rock flour. It's what makes glacial meltwater look milky. Abrasion also polishes the bedrock smooth and cuts parallel grooves called glacial striations.
Scratches showing the flow direction.
Exactly. Sometimes you get bigger channels called glacial grooves or crescent-shaped chips called chatter marks. In whip-based glaciers, pressurized meltwater carrying sediment can also carve channels under the ice.
Okay, abrasion. What else?
Glacial plucking or quarrying. Meltwater seeps into cracks in the bedrock, refreezes, expands, and pries blocks of rock loose. The moving ice then freezes onto these blocks and carries them away.
Like pulling teeth from the rock.
Good analogy. And there's also incorporation, where the ice just surrounds and lifts away loose debris. Plus, at the very front of an advancing glacier, it can bulldoze loose material in a process called plowing.
Abrasion, plucking, incorporation, plowing. Got it. So what specific landforms result from all this carving, especially by mountain glaciers?
They create some really dramatic scenery. We mentioned cirques, those armchair-shaped basins carved near the mountaintop where the glacier originated. Often they hold little lakes called tarns after the ice melts.
Right, the starting bowls.
And arêtes, those sharp ridges between cirques or parallel glacial valleys. And horns, the pyramid peaks like the Matterhorn, where several cirques eat back towards each other.
And the U-shaped valleys, of course.
The classic U-shaped valleys, yes. Much wider and steeper-sided than the V-shaped valleys rivers typically carve. The glacier erodes both the bottom and the sides very effectively.
What about hanging valleys? I remember seeing waterfalls plunging out of side valleys high up on the wall of Yosemite.
Exactly. That's a hanging valley. It happens because the main, bigger glacier erodes its valley much deeper than the smaller tributary glaciers that flow into it. When the ice melts, the tributary valleys are left hanging high above the main valley floor.
And the streams flowing out of them become waterfalls. Cool. Any other mountain features?
Truncated spurs. As the main glacier straightens and widens its valley, it cuts off the ends of the ridges, spurs, that used to jut into the valley between tributary streams.
Okay, that makes sense. Now, what about continental ice sheets? Do they make U-shaped valleys?
Not usually, because they aren't confined to valleys. They tend to create more widespread, lower relief erosional features. They can polish and striate vast areas of flat bedrock, like across the Canadian Shield.
Smoothing things out more.
Yes, or creating streamlined shapes. A classic feature is the roche-moutonné. It's a bedrock hill that's been overridden by the ice. It typically has a smooth, gentle, abraded slope on the upstream side where the ice rode up, and a steeper, rougher plucked slope on the downstream side where the ice pulled rock away.
Asymmetrical, like a sheep lying down, apparently. That's what moutonné means.
Something like that. Another one is a crag and tail. This forms when a resistant knob of rock, the crag, protects a tail of softer rock or sediment downstream from it. Edinburgh Castle is built on a famous crag and tail.
Ah, interesting. And fjords, those deep coastal inlets. Are they glacial too?
Absolutely. Fjords are basically U-shaped glacial valleys that were carved so deep by coastal glaciers, often during ice ages when sea level was lower, that they ended up below sea level. When the glaciers melted and sea level rose, the sea flooded in.
creating those incredibly deep, steep-sided inlets we see in places like Norway, New Zealand, Alaska.
Exactly. Classic glacial erosional features drowned by the sea.
Okay, so glaciers are amazing sculptors, but they also carry all that eroded debris. Where does it all end up? You mentioned moraines earlier.
Right. All that rock and sediment transported by the glacier is called glacial drift, a historical term from the old flood theory days. The stuff deposited directly by the ice, unsorted, is called till, and moraines are landforms made primarily of till.
So different kinds of moraines.
Yes. As the glacier flows, debris scraped off the valley walls or falling onto the edges accumulates along the sides as ridges. Those are lateral moraines.
Like bathtub rings along the valley sides after the ice melts.
Good description. Then, if two valley glaciers merge, their adjacent lateral moraines join up and form a dark stripe of debris running down the middle of the combined glacier. That's a medial moraine. A big glacier fed by many tributaries can have several parallel medial moraines.
Okay, lateral on the sides, medial in the middle. What about at the end?
At the toe, or terminus, where the ice is melting, all the debris being carried by the glacial conveyor belt gets dumped in a ridge. That's an end moraine.
Marking the edge of the ice.
Exactly. The end moraine that marks the farthest advance of the glacier is called the terminal moraine. Long Island and Cape Cod are basically large terminal moraines from the last ice age.
Wow. And if the glacier pauses during its retreat?
It can build another end moraine at that pause point. Those are called recessional moraines. You can often see a series of them traced in the glacier's retreat history.
So moraines are piles of till left by the ice. What other kinds of glacial deposits are there? Is it all just unsorted till?
No, there's also stratified drift sediments deposited by glacial meltwater, which does sort the material by size.
Ah, water sorting things out. Like what?
Glacial outwash is a big one. Meltwater streams flowing away from the glacier pick up till and redeposit it as layers of sand and gravel, often in broad plains called outwash plains or valley trains downstream from the ice. These streams are often braided, with many shifting channels.
Okay, outwash.
Loess, that's very fine silt and clay, essentially rock flour, picked up by strong winds blowing off the cold, dense air over the ice sheets. It can be carried long distances and deposited in thick, unlayered blankets. Large areas of the U.S. Midwest and China have thick loess deposits.
Windblown glacial dust.
Pretty much. Then you have glacial lake sediments. Meltwater often forms lakes near the ice margin, and the fine rock flour carried into these lakes settles out slowly on the lake bed.
And sometimes forms layers, varves.
Exactly. Varves are annual layers, typically a coarser silt layer deposited during summer melt, and a finer clay layer settling out in winter when the lake is still or frozen. They're like tree rings for glacial lakes.
Cool. Any other types? What are cames and eskers? They sound a bit obscure.
They're distinct landforms made of stratified drift. Cames are mounds or ridges of sand and gravel that form when meltwater deposits sediment and depressions on the glacier surface or along the margins. When the ice melts, these deposits are left behind as hills.
So sediment piled up on or against the ice. And eskers.
Eskers are really interesting. They're long, winding ridges of sand and gravel. They formed from the deposits of meltwater streams that flowed in tunnels underneath the glacier. When the ice melts away, the sediment that filled the tunnel is left as a snake-like ridge across the landscape.
A cast of a subglacial riverbed.
That's a great way to put it. They can run for many kilometers.
So imagine you're back around 12,000 years ago. The big ice sheets are melting back across Canada or Scandinavia. What depositional landscape would you see right near the retreating ice?
It would be a dynamic and probably pretty messy place. You'd see the ice front, maybe with meltwater rivers pouring out. You definitely see low ridges, the end moraines marking recent positions of the ice.
Moraines check.
The land the ice has just retreated from would likely be hummocky. Uneven ground covered in a layer of till that's ground moraine.
Okay, bumpy till plains.
Lots of water around. Braided streams choked with milky-looking sediment, the outwash. Ponds and lakes filling depressions. Maybe kettle lakes formed where big chunks of ice got buried in the outwash and then melted, leaving holes.
Kettle holes, got it.
You might see streamlined, elongated hills made of till, oriented with the ice flow. Those are drumlins. And maybe some of those winding esker ridges snaking across the ground moraine. Perhaps some came mounds, too.
Drumlins, eskers, cames, kettles, moraines, outwash. Quite a collection.
It's a whole suite of landforms. And maybe dusty air, if winds are picking up loess. It would look very different from today's landscape. And importantly, those esker, came, and outwash deposits are great sources of sand and gravel for construction today. And old glacial lake beds often made very fertile farmland.
So these ice sheets didn't just reshape the surface, their deposits are useful too. But what about the sheer weight of all that ice? Did it affect the land itself, like the crust?
Oh, profoundly. Continental ice sheets are incredibly heavy, kilometers thick over vast areas. That weight actually pushes the Earth's lithosphere, the rigid outer shell, down into the softer, more fluid asthenosphere beneath it.
The land sinks under the ice.
Yes, it's called glacial subsidence or isostatic depression. Think of placing a heavy book on a soft mattress that sinks down. The rock surface under central Greenland and Antarctica is actually below sea level today because it's still depressed by the remaining ice weight.
Wow. So what happens when the ice melts? Does it just pop back up?
It does rebound, but very, very slowly. It's called post-glacial rebound or isostatic rebound. As the weight is removed, the displaced asthenosphere slowly flows back underneath, lifting the lithosphere back up.
Like the mattress slowly regaining its shape after you remove the book?
Exactly. But because the asthenosphere flows so slowly, it's rock. After all, even if it's somewhat fluid over long timescales, the rebound takes thousands of years. It's still happening today in places like Scandinavia and Canada that were covered by the last ice sheets.
We can measure it.
Yep, with GPS. We see the land rising, sometimes by centimeters per year. In coastal areas, this rebound lifts old beaches and shorelines high above the current sea level, forming raised beach terraces.
Incredible. And all that water locked up in ice, that must affect sea level globally, right?
Hugely.
Yep.
Glaciers and ice sheets are Earth's largest reservoir of fresh water outside the oceans themselves. When ice sheets grow, they take water out of the oceans, causing global sea level to fall.
How much did it fall during the last ice age?
Estimates vary, but potentially by as much as 100 to 120 meters, that's over 300 feet.
Whoa, that would expose a lot of land that's currently underwater.
It did. Vast areas of the continental shelves became dry land. Coastlines were hundreds of kilometers farther out in many places. Land bridges formed, like the one connecting Siberia and Alaska across the Bering Strait, allowing humans and animals to migrate between continents.
So people could walk from Asia to North America.
That's the prevailing theory, yes.
Yeah.
We even find submerged evidence of human occupation from that time on the continental shelf off the U.S. East Coast now.
And conversely, when the ice melts,
The water returns to the oceans, and sea level rises. If all the ice in Greenland and Antarctica melted today, global sea level would rise by something like 70 meters.
70 meters, that would flood coastal cities worldwide. London, New York, Shanghai.
Gone. It would be catastrophic. That's why understanding ice sheet stability is so critical today.
Definitely. Okay, besides sea level, how else did glaciation affect water systems? Rivers, lakes.
Glaciers completely rerouted drainage systems. Ice sheets acted like giant dams, blocking rivers, forcing them into new courses. Moraines left behind after melting could also dam valleys, creating lakes.
So the map of rivers in North America, for instance, was changed by the ice.
Dramatically. Before the ice ages, many rivers in central North America drained northward towards the Arctic. The ice forced them south, establishing the precursors of the modern Ohio and Missouri rivers flowing into the Mississippi.
And it created new lakes, too, not just the Great Lakes.
Oh, countless thousands of smaller lakes were formed by glacial action kettle lakes in scoured bedrock depressions on the Canadian Shield. And sometimes huge but temporary lakes formed, dammed by the ice itself or by moraines.
Like Lake Missoula, I've heard about the floods from that.
Exactly. Glacial Lake Missoula in Montana was dammed by an ice lobe. When that ice dam failed repeatedly, it unleashed catastrophic outburst floods, Alps, that scoured the channeled scablands of eastern Washington state. Incredible erosive power.
Leaving behind giant ripple marks and stuff.
Giant current ripples, dry waterfalls, huge displaced boulders, evidence of unimaginable floods. Similar massive lakes existed elsewhere, like Glacial Lake Agassiz, which covered a huge area of central Canada and the northern U.S., dammed by the Laurentide ice sheet. Its drainage events would also have been enormous.
What about areas beyond the ice edge? Were they affected? Pluvial lakes.
Yes, regions south of the ice sheets often became wetter during glacial periods, possibly due to shifts in atmospheric circulation. This led to the formation of large pluvial lakes in areas that are deserts or semi-deserts today.
Like in the western U.S.
Yeah, the Great Basin area had huge lakes. Lake Bonneville was enormous. The Great Salt Lake is just a tiny remnant. You can see the old shorelines of Lake Bonneville etched high up on the mountainsides around Salt Lake City.
Wow. And the environment right next to the ice. Periglacial. Permafrost.
Right. The zone bordering the ice sheets was extremely cold, leading to the formation of permafrost, permanently frozen ground, potentially hundreds or even thousands of meters deep.
Like in Siberia or northern Canada today?
Exactly. These periglacial environments have unique features caused by the intense freezing and thawing cycles in the upper layer of soil, the active layer. You get patterned ground, where the surface cracks into polygons. Ice wedges form in the cracks.
Stone circles, too.
Sometimes, yeah. Frost heaves can push larger stones upwards and outwards, arranging them into circles or polygons over time. And of course, permafrost creates huge challenges for construction because if it thaws, the ground turns to mud and subsides.
Hence, buildings on stilts and elevated pipelines in places like Alaska.
Precisely, to keep the ground frozen.
Okay, so let's zoom in on the Pleistocene Ice Age itself. This period from about 2.6 million years ago to roughly 12,000 years ago. We know ice covered huge areas. How far south did it reach in North America?
Evidence like erratics and striated bedrock in Central Park, New York City, shows the ice came that far south. The main Laurentide ice sheet covered almost all of Canada east of the Rockies and pushed down into the northern U.S., reaching roughly the line of the Ohio and Missouri rivers.
And it merged with other ice sheets?
Yeah, it merged with the Greenland ice sheet to the northeast and the Cordilleran ice sheet that covered the mountains of western Canada and southern Alaska. It was an enormous complex, and smaller ice caps and valley glaciers expanded in the Rockies, Sierras, and Cascades further south.
What about Europe and Asia?
Massive ice sheet centered over Scandinavia spread south over northern Germany and Poland, west across the UK and Ireland, and east into Russia. Smaller ice sheets existed in Siberia, and glaciers expanded significantly in the Alps, Himalayas, and other mountains.
But not much in the southern hemisphere apart from Antarctica.
Antarctica remained ice-covered, and mountain glaciers grew in the Andes and New Zealand, but no major continental ice sheets formed over South America, Africa, or Australia.
Got it. And the oceans? Lots of sea ice.
Much more extensive sea ice, yes, covering the Arctic Ocean and extending much farther south in the North Atlantic than it does today.
What was life like during the Pleistocene? For animals, plants, humans?
Colder, obviously. Climate zones shifted south. Tundra covered large parts of Europe and North America that are forested today. Conifer forests dominated areas that are now temperate grasslands or deciduous forests.
Wetter in some places, drier in others.
Generally wetter near the ice sheets, pluvial lakes, but perhaps drier in some equatorial regions, causing rainforests to shrink. It was probably windier globally, too, kicking up all that ludus dust.
And the megafauna? Mammoths, mastodons?
Woolly rhinos, giant sloths, saber-toothed cats. A whole range of large mammals adapted to colder conditions, many of which went extinct around the end of the last glacial period.
And humans? Were Homo sapiens around?
Our species evolved during the Pleistocene. Early human ancestors existed at the start, and Homo sapiens had spread across most of the globe, except Antarctica, by the end. They survived the ice ages using fire, tools, and likely migrating across those exposed land bridges.
Now, Agassiz thought one ice age, but we know now it was cyclical, right? Glacials and interglacial.
Exactly. Studying layers of glacial deposits on land revealed buried soils, paleosols, and fossils from warmer periods between the layers of till. This showed multiple advances in retreats.
Glaciations and interglacials.
Right. Radiometric dating confirmed these cycles. Europe has its traditional names for glacial stages: Würm, Riss, Mindel, Günz. North America had Wisconsinan, Illinoisan, Kansan, Nebraskan, though the older ones are now grouped.
But the real picture is even more complex.
Oh yeah. When scientists started analyzing deep-sea sediment cores, looking at the chemistry of tiny fossil shells, especially oxygen isotopes, which reflect temperature and ice volume, they found evidence for way more cycles. Maybe 20 or 30 significant interglacial fluctuations over the last 2.6 million years. The traditional land-based stages are probably just the biggest, most prominent ones.
So if you want to see evidence of all this glaciation today, where should you go? Besides maybe Central Park.
Well, if you want to see active glaciers, you need to go to high latitudes or high altitudes. Greenland and Antarctica for the big ice sheets, though they're hard to access.
Easier options.
Mountain glaciers are much more accessible. Alaska has fantastic glaciers, many reaching the sea. The European Alps, the Andes in South America, the Southern Alps of New Zealand. You can see active glaciers in all those places, sometimes even from cruise ships or easily accessible viewpoints.
And for the landscapes carved by past glaciers.
North America is full of them. The Great Lakes are fundamentally glacially scoured basins. The Finger Lakes in New York are glacially deepened valleys. You can see drumlins near Rochester, NY, moraines across Illinois, the polished, scoured Canadian Shield. Many U.S. and Canadian national parks showcase spectacular glacial features.
Like which ones?
Glacier National Park in Montana, incredible cirques, U-shaped valleys, arêtes, horns, though its namesake glaciers are rapidly shrinking. Yosemite for that classic U-shaped valley and hanging waterfalls. Voyageurs National Park in Minnesota shows the scouring of the Canadian Shield. Acadia in Maine has smoothed granite hills, Roche-Montagne, and small fjords. Glacier Bay in Alaska lets you see tidewater glaciers calving today, plus all the features left by recent retreat.
Lots of options for seeing glacial impacts, past and present. Okay, the big question then, what causes these ice ages? Why does the climate swing between glacial and interglacial periods?
It's a combination of factors operating on different timescales. We need to think about long-term controls that set the stage for ice ages and short-term triggers that drive the cycles within them.
Long term first. What makes the Earth susceptible to ice ages at certain times in its history, but not others?
Plate tectonics is key. The arrangement of continents matters. You need large land masses at high latitudes for big ice sheets to form on. If all the continents are clustered near the equator, it's hard to get an ice age going.
Makes sense. Location, location, location.
Also, the configuration of continents affects ocean currents, which transport heat around the globe. For example, when Antarctica got isolated by continental drift, the Antarctic circumpolar current developed, thermally isolating the continent and allowing the ice sheet to grow and stabilize.
So ocean gateways opening or closing are important.
Very. Plate tectonics also influences sea level over long timescales. E.g., faster seafloor spreading creates larger mid-ocean ridges, displacing water and raising sea level. Higher sea level means less land area for glaciers. And mountain building, like the Himalayas, can affect atmospheric circulation and maybe even CO2 levels through increased weathering.
CO2, that's the other big long-term factor, right? Greenhouse gases.
Absolutely crucial. Carbon dioxide is a major greenhouse gas. Higher CO2 levels generally mean a warmer planet, making it very difficult for large ice sheets to persist. Lower CO2 levels favor colder conditions and glaciation.
What controls CO2 over millions of years?
Things like volcanic activity releases CO2, chemical weathering of rocks consumes CO2, the burial of organic carbon like in coal swamps, which removes CO2, and the activity of photosynthetic organisms. Long-term changes in these processes shift the baseline climate.
So we've had ice ages before the Pleistocene. You mentioned the Permian and snowball Earth.
Yes, the rock record shows evidence stillites, striated surfaces for several older ice ages. The Permian, 280 million years ago, is well documented, linked partly to the supercontinent Pangaea having large parts over the South Pole. And there's evidence for a very extensive, possibly global glaciation back in the late Proterozoic, around 600, 700 million years ago, the snowball Earth episodes, maybe even earlier ones too. Ice ages are recurrent but not constant features of Earth history.
Okay, so long-term factors set the stage. What triggers the relatively rapid back-and-forth cycles within an ice age, like the Pleistocene ones?
That's where the Milankovitch cycles come in, named after Milutin Milankovitch, a Serbian scientist.
I've heard of those, changes in Earth's orbit.
Exactly. 3 main cycles. 1, eccentricity. Earth orbit changes shape from nearly circular to more elliptical and back over about 100,000 years. 2, obliquity, tilt. The tilt of Earth's axis varies between about 22.5 and 24.5 degrees over roughly 41,000 years. Affects the intensity of seasons. 3, precession. Earth's axis wobbles like a spinning top over about 23,000 years. Affects when seasons occur relative to Earth's position in orbit. For example, whether summer happens when Earth is closest or farthest from the sun.
And these subtle orbital changes affect climate.
They affect the distribution of solar energy, insolation, received by Earth, especially at different latitudes and seasons. Milankovitch calculated that these cycles cause significant variations in summer sunlight in the critical mid to high northern latitudes where ice sheets grow.
So cooler summers mean less snow melts, allowing ice sheets to grow. Warmer summers mean more melting and retreat.
That's the core idea. And the timing of glacial cycles recorded in ice cores and ocean sediments matches the frequencies of the Milankovitch cycles remarkably well. They seem to act as the pacemaker for the glacial-interglacial rhythm.
But are they strong enough on their own to cause such huge climate shifts?
Probably not entirely. The direct temperature change from Milankovitch forcing alone might only be a few degrees Celsius. Most scientists think other factors within the Earth system amplify these orbital signals.
Feedback loops, like the albedo effect you mentioned.
Exactly. More ice, higher albedo, more cooling, more ice. That's a positive feedback. Changes in greenhouse gas concentrations, CO2, methane, also act as strong feedbacks. Ice cores show they rise and fall closely in sync with temperature.
How do CO2 levels change with the cycles?
It's complex, involving changes in ocean circulation, marine biology, vegetation on land. Colder oceans can absorb more CO2, for example. Changes in ocean currents, like the thermohalian circulation, the global ocean conveyor belt, can also amplify climate shifts by changing how heat is transported.
So orbital cycles provide the initial push or pull, and then Earth's own systems run with it.
That's a good way to think about it.
Yeah.
Milankovitch cycles are the trigger, but feedbacks involving ice albedo, greenhouse gases, and ocean currents determine the magnitude of the climate swing.
Could we put together a rough story for the Pleistocene then? Long-term cooling setting the stage?
Right. Earth's climate was generally cooling through the Cenozoic era from the warm Eocene, 50 million years ago. Antarctica became glaciated maybe 34 million years ago, likely linked to tectonic shifts, isolating it and starting the cold circumpolar current.
But the northern hemisphere didn't get major ice sheets until much later.
Not really until the start of the Pleistocene, 2.6 million years ago. Why then? Still debated, but maybe related to ongoing cooling plus a specific trigger. One idea involves the closure of the Isthmus of Panama around that time.
How would closing the gap between North and South America affect northern ice sheets?
It dramatically changed ocean currents. It strengthened the Gulf Stream, bringing more warm, moist water up into the North Atlantic. Paradoxically, this increased moisture supply might have provided the heavy snowfall needed to build the Laurentide ice sheet in the already cold Canadian Arctic.
More moisture for snow. Interesting. So the stage is set, the Arctic is cold, maybe getting snowier. Then the Milankovitch cycles kick in.
Exactly. They start driving the advances and retreats. Imagine a simplified cycle for the Laurentide ice sheet.
Advance. Orbital cycles favor cooler summers. Snow accumulates year after year, turns to ice. Growing ice sheet increases albedo, causing more cooling, feedback. It starts to flow outwards.
Getting bigger and bigger.
Stage 2. Maximum. It grows huge, maybe kilometers thick. But its own weight causes the land beneath to subside, lowering its surface elevation. Maybe extensive sea ice forms in the North Atlantic, cutting off some moisture supply. The glacier might reach a sort of equilibrium or even start to stagnate. Maybe it gets too big for its own good.
Choking on its success.
Possibly. Then stage 3. Retreat. Orbital cycles shift towards warmer summers. Sea ice melts back. Crucially, precipitation might start falling as rain on the lower parts of the ice sheet in summer. Rain is very effective at melting ice.
Much more than just warm air.
Much more. So warming temperatures plus summer rain can lead to rapid melting and retreat of the ice margin. The whole cycle might take roughly 100,000 years, matching the dominant eccentricity cycle, but with influences from the shorter tilt and precession cycles too.
So, based on these cycles, where are we now? Are we due for another glacial period soon?
That's the multi-million-dollar question. Typical interglacials in the Pleistocene lasted maybe 10,000 to 20,000 years. Our current one, the Holocene, has been going for about 12,000 years. So, based purely on natural cycles, you might expect the Earth to be slowly heading towards cooler conditions. But we've thrown a huge wrench in the works with anthropogenic greenhouse gas emissions. The massive increase in atmospheric CO2 since the Industrial Revolution is causing rapid warming that's overwhelming the subtle orbital influences right now.
So human activity is overriding the natural cycle.
It seems to be, at least for the foreseeable future. Instead of cooling, we're warming rapidly. Glaciers worldwide are retreating, ice sheets are losing mass at accelerating rates. We might be heading into a super-interglacial, potentially delaying the next ice age by tens or even hundreds of thousands of years.
Unless we dramatically change our emissions trajectory.
Exactly. There was the Little Ice Age, a cooler period from about 1300 to 1850, where glaciers advanced significantly in many places. That shows the system can still fluctuate. But the warming trend over the last 150 years is very pronounced and strongly linked to human activity.
And the worry is continued warming leading to more ice melt and significant sea level rise.
That's the major concern, yes. Especially the stability of the West Antarctic ice sheet, which is grounded below sea level and potentially vulnerable to rapid collapse. As we said, if all the ice melts, we're looking at 70 meters of sea level rise.
Which would reshape coastlines globally.
Fundamentally. So whether the long-term future holds an ice house or a greenhouse, Earth is uncertain and depends heavily on our actions, but the near-term reality is ongoing warming and glacial retreat.
Wow. Okay, well, this has been an incredible journey through ice and time. We started with those mysterious wandering boulders.
And ended up discussing orbital mechanics, deep-sea sediments, and humanity's impact on the planet's climate system.
We covered the nature of ice itself, how glaciers form, move, and dramatically sculpt the land through erosion, leaving behind things like U-shaped valleys and fjords.
And how they deposit vast amounts of material, creating moraines, eskers, drumlins, and fertile plains. We looked at the evidence for the Pleistocene Ice Age, its multiple cycles, and how life adapted.
And we explored the complex causes, the long-term geological factors, like plate tectonics and CO2, and the shorter-term Milankovitch cycle acting as the pacemaker, all amplified by Earth's internal feedbacks.
It really shows how interconnected everything is in the Earth system. Those erratics weren't just random rocks, they were clues to a planetary history shaped by ice.
Absolutely. So maybe a final thought for everyone listening. We've seen how dramatically Earth's climate has shifted in the past due to natural forces. Now, we understand that human activities are driving rapid changes today. Given this knowledge, what responsibility do we have collectively and individually in navigating the future of our changing planet?
That's definitely something to ponder. The story of ice is not just about the past, it's very much about our present and our future.